Welcome to the video podcast regarding specific and latent heat calculations. Time for your turn problems. For these, I recommend that you be ready to pause the podcast, have a pencil and paper and calculator handy. Hopefully you have your equations and constants written down from earlier. Read the problem, write your data table, solve the problem, and then resume the podcast and see if your solution matches up with mine. On this first problem, we're going to calculate how much heat must be removed from a 125 gram sample of water to lower its temperature from 50 degrees Celsius to 5 degrees Celsius. Welcome back. Let's take a look at how you did. You're going to notice here that I'm going to show you the solution, but I'm not going to show you my data table. The reason for that is we have done a lot of data tables together as we work through this podcast. If data tables are a particular problem for you, I would recommend that you rewind the podcast back to the beginning and work slowly through those problems again, making sure that you pause before I show you the data table. Try it for yourself and see how that goes. Now, we're trying to find out how much heat must be removed from that 125 gram sample of water. So the equation that we're going to use will have our specific heat in it and the change in temperature. So Q will equal mass times specific heat times the change in temperature. Our mass was 125 grams. We're going to multiply that times 4.184 joules per gram times degrees Celsius. And then notice here that TF minus T naught, our final temperature minus our initial temperature, is a negative number because this is cooling. So it's times negative 45 degrees Celsius. Our value is negative 23,535 joules. The degrees Celsius and grams cancel, so we know we set up our equation correctly, and then we just want to adjust this to the correct number of significant digits. So Q would equal negative 23,500 joules. Let's try another problem. Here we have a 20 gram sample of a metal that's removed from a boiling water bath and placed in a calorimeter containing 50 grams of water at 20 degrees Celsius. The final temperature of the calorimeter water is 22.5 degrees Celsius. What is the specific heat of the metal? Now, we did not do a problem exactly like this, but this is very similar to the problem where we added warmer water to cooler water. You will want to, as a hint, set up a data table that shows the heat being lost. In this case, the heat being lost is by the metal and the heat being gained by the water. If you set those up in that same way, you should be able to solve for the one value that you're missing as you set up the heat loss equals, the opposite of heat loss equals heat gain equations. The one value you're missing here is the specific heat of the metal. This actually is simpler, and you'll see that when you set the two equations up opposite each other. So there's your hint. Go ahead and pause the podcast, write your data table, and solve the problem, and I'll see you in a few minutes. Well, let's see how you did. Welcome back. First, let's calculate the heat, or Q, gained by the water in the calorimeter. So we take our Q is equal to the mass times the specific heat times the change in temperature. This is equal to 50 grams times 4.184 joules per gram times degrees Celsius times the 2.5 degrees Celsius gain in temperature. The degrees Celsius will cancel, the grams will cancel, and we're left with 523 joules. Now this heat gained by the water came from the metal because this was done in a calorimeter, which isolates the system from the surroundings. So, because the heat gained by the water is equal to the opposite of the heat lost by the metal, Q for the metal would be minus 523 joules. Since we now have Q for the metal, we have its mass, and we have its change in temperature, we can solve for the specific heat. An inference has to be made with the metal that its initial temperature, because it's being removed from boiling water, was 100 degrees Celsius. So our change in temperature for the metal was 22.5 degrees Celsius minus 100 degrees Celsius, which gives us a temperature change of minus 77.5 degrees Celsius. We're now ready to go ahead and solve for the specific heat. So we take our value for Q, divided by the product of the mass times the change in temperature. So minus 523 joules divided by 20 grams, and then take that value and divide it by minus 77.5 degrees Celsius, and you get a specific heat for the metal of 0.337 joules per gram times degrees Celsius. Now, because you have a negative Q value and a negative temperature change, those cancel, and you're left with a positive value for specific heat. Specific heat will not be negative. Always report specific heat as a positive number. If you get a negative value for it, then you need to go back into your equation and check to see where you may have missed a sign. Okay, so take a look at that, and remember here that Q is negative for the metal because it lost heat in this system. Ready for another problem here. We have a 50-gram piece of iron that has a temperature of 85 degrees Celsius, and it's placed in a calorimeter containing 200 grams of water at 10 degrees Celsius. We want to know what the final temperature of the water is. The specific heat of iron is 0.450 joules per gram times degrees Celsius. So at this point, you can go ahead and pause the podcast, write your data table, and solve the problem, and I'll look forward to seeing you back here in just a moment. The key to solving this problem is to make sure that you know and demonstrate in your data table and the way you set up your equations that the opposite of heat loss is equal to heat gain. So you can see I have the equation set up, the heat loss in a bracket with a negative sign outside it. The heat gain can just be set up normally, and here instead of having just delta T, we have delta T expanded to TF minus T naught, since TF is the value we're trying to solve for. So we take the opposite of our heat loss, which is the 50 grams times 0.450 joules per gram times degrees Celsius, times TF minus 85 degrees Celsius, and we set that equal to 200 grams times 4.184 joules per gram times degrees Celsius times TF minus 10 degrees Celsius. So on the heat loss side, inside the brackets with a negative sign outside it, we have 22.5 joules per degree Celsius TF minus 1912.5 joules, set equal to 836.8 joules per degree Celsius TF minus 8,368 joules. We're going to go ahead and multiply through the heat loss side by -1 so that we can get rid of that negative sign outside the bracket, and when we do that, it will make the 1912.5 joules positive, and we set up the equation so that it's subtracting the 22.5 joules per degree Celsius TF, and that is still equal to 836.8 joules per degree Celsius TF minus 8,368 joules. And we're going to go ahead and combine the like terms and rearrange the equations so that we can solve, and you'll see that on the next slide. We have some more algebra to do before we get to the end of this problem, so we're going to add 8,368 joules to both sides of the equation so that it cancels off the heat gain side and is added to the heat loss side, where it can be combined with the 1912.5 joules. And then the 22.5 joules per degree Celsius TF, we add that to both sides so it cancels out on the heat loss side and is added on the heat gain side to the already present 836.8 joules per degree Celsius TF. So combining those like terms, we have 10,280.5 joules is equal to 859.3 joules per degree Celsius TF. We want to isolate TF, so we divide both sides of the equation by 859.3 joules per degree Celsius. When we do that, it cancels on the right side of the equation, and then on the left side we divide our 10,280.5 joules by the 859.3 joules per degree Celsius. The joules cancel. We're left with 1 over 1 over degree Celsius, which is the unit for temperature final, and our final temperature is 12 degrees Celsius. Let's do one more problem together. Here we have 135 grams of steam at 175 degrees Celsius. It's captured in a refrigeration system that transforms it to ice at negative 10 degrees Celsius. How much heat does the refrigeration system remove to achieve this transformation? Now, this is very similar to the problem where we took negative 20 degrees Celsius ice and converted it to steam at 225 degrees Celsius. The difference is we're removing heat and lowering temperature and condensing and then freezing rather than melting and boiling as we did in the previous problem. But I'll give you a hint. There are 5 steps here. If you break it up into the 5 steps, this should go well for you. Welcome back. Let's see how you did. The first step, of course, was to change the steam or water vapor at 175 degrees Celsius to steam at 100 degrees Celsius. So we use our equation that involves specific heat of steam and change of temperature. So we took our 135 grams of steam times the specific heat of water vapor or steam, which is 2.080 joules per gram times degrees Celsius. And then the temperature change here is minus 75 degrees Celsius. So our heat change will be negative. We're removing heat from the system, and we get a value of 21,060 joules. Or 21,060 joules would be a much more intelligent way to say that. Now that we have our steam at 100 degrees Celsius, we want to condense it to liquid water at 100 degrees Celsius. So our next step will involve an equation that relates the latent heat of vaporization with our mass to find heat. So we're going to take our 135 grams and multiply it times negative 2260 joules per gram. The negative sign here because we're condensing the steam by removing heat from it. When we do this, we get a value of negative 305,100 joules. Again, look at the tremendous amount of heat that's involved in a phase change between a gas and a liquid. Our next step, now that we have our liquid water at 100 degrees Celsius, is to take it down to liquid water at 0 degrees Celsius so we can get ready to freeze it. So again, we use an equation that relates the specific heat of liquid water, change in temperature and mass. So we take our 135 gram mass of water times 4.184 joules per gram times degrees Celsius, the specific heat of liquid water, and times negative 100 degrees Celsius. Again, the change in temperature here would be the temperature final 0 degrees minus the initial temperature of 100 degrees Celsius, so you get a negative change in temperature. And our final value here, final quantity, is negative 56,484 joules. Now that we have our water, liquid water at 0 degrees Celsius, we want to take it to solid water or ice at 0 degrees Celsius. So here we need to calculate Q using our latent heat of fusion. And so we're going to take our mass times the latent heat of fusion, and that's going to be equal to 135 grams times negative 334 joules per gram, and that will equal negative 45,090 joules. Now again, our latent heat of fusion has a negative sign here because we're removing heat and freezing this water. Our last step is to take the ice at 0 degrees Celsius down to a temperature of minus 10 degrees Celsius. So we need to use the equation that relates the specific heat of ice to the change in temperature and its mass. So we'll take 135 grams times the specific heat of ice, which is 2.050 joules per gram times degrees Celsius, times the negative 10 degrees Celsius temperature change. So when we calculate that, notice that our grams will cancel, our degrees Celsius will cancel, and we'll get a value of negative 2,767.5 joules. We've got all 5 steps taken care of, so what we want to do is find the sum of those steps. Now, very important as you add these that you remember to put the negative sign in front of each of these values because heat has been removed in each step. So we'll add our negative 21,060 joules plus negative 305,100 joules plus negative 56,484 joules plus negative 45,090 joules plus negative 2,767.5 joules. This gives us a value of 430,501 joules and please make that a negative 430,501 joules. We'll adjust that for significant digits so that we have 3, and adjusted it will be negative 431,000 joules. I hope you did well with that. If you are having problems with these, rewatch the podcast. Pause often, work out your own data tables, redo the solutions, and good luck with that. These are not problems that are undoable, but they are problems with some complexity that will require patience on your part as you work through them. So I wish you well. Thanks. This is the end of part 4 of the specific and latent heat problem solving video podcast here at Ontario High School. Part 5 is to come. I want to leave you with a quote from Thomas Jefferson. Bodily decay is gloomy in prospect, but of all human contemplations the most abhorrent is body without mind. Good luck.